Hello everyone, my name is Wojciech Rejchel. I am from the Nikolaus Copernicus University in Theorem in Poland. My talk is about the fast and robust procedures in high-dimensional variable selection. This talk is based on two papers, the first one with Małgorzata Bogdan from University of Wrocław in Poland, and the second one with Konrad Furmańczyk from the Warsaw University of Life Science, also in Poland. In the talk, I will focus on the so-called single index model, where we have the following notations. Y is the response variable, X is a vector of predictors, so we have P predictors, beta is the true parameter, we have also random errors, and the function G is unknown. So we assume that the relation between predictors and response variables is given by this scalar product and the function G. There are many examples of models which are contained in the single index model, for instance, the linear model or modified linear models, or the binary regression or binary classification. So we assume that y takes only two values, say 0, 1, and the probability of being 1 given x is given by the function g and scalar product again. So, for instance, we have logistic model. Here we have the probit model also here. Okay, so this is the single index model, and our task is to find significant variables which are contained in the set T. So these are coordinates of the beta vector, the true parameter, which are non-zero. And we want to do it even if the number of predictors P is much larger than the sample size N. So we work in the high dimensional case. Of course, the function G is unknown, so the true parameter is not identifiable. However, it is not a problem. I will show you that under my assumptions, this parameter can be recognized up to a positive multiplicative number, which is indeed all we need, because we want only to be able to recognize which coordinates are zero, which are non-zero. We are not going to estimate magnitudes of these coordinates. Okay, so we work in the single index model. So we put no assumptions on distribution of errors, on the we do not need existence of their moments and so on. The function G is unknown. It will not be used in the estimation process. From the theoretical point of view, all we need is that it is increasing with respect to the first variable where we have predictors. Okay, but so this is all we need. Yeah, in the binary regression case, again, the function G is unknown and it is not used in the estimation process. So our task is to find the procedure which is robust with respect to distribution of errors, with respect to the function G, and computationally fast. If we focus on a moment on the linear model, then there is a very popular estimator called lasso, which is a minimizer of the sum of two functions. The first one is the risk, and the second one is the penalty, which is the L1 penalty. I think most of you are familiar with this estimator and its properties. And you also know that this estimator is very sensitive with respect to the distribution of errors. For instance, it doesn't work well if there are some outliers in the sample. So what people do in such cases, they, for instance, can use the least absolute deviation estimator with the penalty, which looks like that. Again, we minimize the sum of two functions. The first one is risk, then there is a penalty, the same penalty as here. But here you've got, instead of quadratic loss, you have the absolute loss. And this estimator is robust. Okay, but the problem is that it is very time consuming if the number of predictors is at around 1,000. Okay, it works very slowly comparing to this estimator. So it was our motivation. I mean, we wanted to find the procedure which is robust as this estimator, but at the same time, it is computationally fast as this estimator. And our idea is very simple, I think. We use ranks, which are very well known in non-parametric statistics. So we take response variables, we sort them from the least to the greatest, we assign ranks to objects, and then we simply put to the lasso estimator, instead of response variables, we put ranks. In fact, ranks divided by n. Okay, so this procedure is extremely simple. Moreover, it is computationally fast. We do not need any new algorithmic machinery. You can use, for instance, the GLMnet package in the R program. It is robust with respect to outliers because we use ranks. It does not need function G. The question is, in fact, what we estimate. I think it's clear that we do not estimate using our rank estimator, we do not estimate the parameter beta. We estimate something else. Okay, in the case of binary regression, our idea is also very simple. We just treat these labels, 0, 1 labels as numeric and put them into the lasso. Now, this is not a new procedure. It was used in the classical statistics. So without high dimensionality, without this penalty, it was used by Fisher in the middle of last century. But again, this is very fast here in the high dimensional case, very fast. We do not need anything new. Again, it's clear that we do not estimate. In the rest of my talk, I will focus only on the estimator based on ranks. However, almost the same can be obtained in a similar fashion if you use this estimator from the binary regression. Okay, so we focus on ranks. So what we estimate? I think it's clear that we estimate something which is denoted by theta 0. This is the minimizer of the risk. In fact, it is the minimizer of expected risk. So this function is non-random, so this is non-random vector. Okay, but again, what is the relation between the parameter beta and theta 0? And you can show that under some standard assumptions plus the function g has to be increasing with respect to the first variable, as I told you before. And there is also one important assumption that for each parameter theta, the conditional expectation of theta times x given beta times x equals to some number times beta times x. So you can think more or less that this conditional expectation is linear with respect to the beta times. So this assumption is very important. It is not new. It was used in in statistics, in estimation, in the 80s of the last century. Moreover, nowadays it is also used in the variable selection. For instance, it is satisfied in the case that we've got only one predictor. So maybe it is not important example. However, it is also satisfied in quite a large family called elliptical distributions. And for instance, the multivariate normal distribution is in this class, the multivariate T distribution is in this class. So this is quite a large class of examples. But what is more, in the nice paper of Holland Lee, it was proven that this condition is very weak, in some sense, asymptotically. And asymptotically means that when p goes to infinity. So this is our case. We work in the high dimensional case, the number of predictors can be large. So this is our case. So they obtained such results that this condition is very, very weak. Okay, and if we have these three conditions, then we can prove that there exists some positive numbers such that on each coordinate, the true parameter is proportional to the parameter that we estimate, which means that the sets of non-zero coordinates of beta and the parameter theta 0 are the same. So if we are able to find non-zero coordinates of theta 0, then we are able to find non-zero coordinates of beta. So we are able to find significant predictors. In general, theoretical properties of our estimator are very similar to standard lasso estimators. So for instance, to be consistent in variable selection, it needs very restrictive assumptions, but to obtain screening or to obtain separability of predictors, it needs much weaker assumptions. Separability means that coordinates of our estimator corresponding to significant predictors are always larger in the absolute value than those corresponding to non-significant predictors. Okay, so this is standard for lasso estimators. However, using ranks, we are able to obtain such results without any assumptions on error terms or the function g. Only we need that it is increasing, the function g is increasing with respect to the first variable. Okay, vertical analysis of rank lasso is more involved than regular lasso because our risk is not a sum of independent random variables, but dependent random variables, because here we got ranks. However, if we use the statistics theory, we can overcome problems with dependence here. Okay, so finally, I will give you only one result, which is quite similar to standard results on lasso estimators. So assumptions are we need that our predictors are sub-Gaussian, which is standard if you work with random predictors. We need some regularity like cone invertibility condition. The sample size has to be large enough, larger than some number. P0 is the number of significant predictors times logarithm of the number of predictors. The tuning parameter has to be also large enough, and here is standard square root of log p by n. And then with high probability, if a is close to to 0, then with high probability we can bound, upper bound the estimation error of the difference between our estimator and the true parameter. So this result is very similar to standard results for lasso estimators. It works in high-dimensional case, but once again, I want to stress that that it does not need any assumptions on the distribution of errors. We do not need function g also. So if you have something like this, the consistency in estimation, then you can use the thresholded estimator or the adaptive lasso to obtain consistency in variable selection under quite weak assumptions. Due to the lack of time, I will finish now. If you want to find some more details about theoretical properties of our estimator or experiments, we have many experiments, many results of experiments that we can go to these two papers and find it. So thank you very much for your attention, and goodbye.